Hi, this video is an introduction to a mathematical operation called the derivative. Some of you may be taking calculus physics concurrently with calculus 1, and you may not have encountered the derivative yet. So this video aims to give you the tools you need to succeed in calculus-based physics regarding the derivative. So the derivative is a mathematical operation that allows you to find the slope of a function at a specific point. Another way of saying that is it's a function. It's an operation that allows you to find the infinitesimal rate of change of a function at a specific point. So it involves finding rates of change. Physics is full of physical quantities that involve rates of change. So you can see why it might be important in a physics class to know how to calculate derivatives. So to motivate what's going on here, I drew a nice smooth function, looks like a polynomial, and y as a function of x. So let's say you want to find the slope of this function at the red dot, the point I labeled x equals a. Well, the mathematical definition of the slope is rise over run, or another way of saying that is change in y over change in x. So to estimate the slope of this function at that red point, we actually need to know the value of this function at 2 points, preferably another point close by. We'll call that point x equals a plus a small amount h, where h is that distance, the horizontal distance between those 2 points. So applying our definition of the slope, this mathematical equation that allows us to find the slope, we can estimate the slope at the point x equals a by finding the difference between the value of the function at f equals a plus h and f equals a, or x equals a, and dividing it by the change in x between those 2 points, which in this case is the same as x. But what we're actually would be finding here, let's find a different color, green, is not the slope of the black line at the red dot labeled x equals a. What we'd actually be finding is the slope of a straight line that passes through those 2 points. So to find a really good estimate of the slope of the black line, the function we're interested in at the point x equals a, using these 2 red dots to estimate the slope, in practice, to get a good estimate, we got to make the distance between those 2 dots, the distance between these 2 points, h, as small as possible. And making h as small as possible is saying let's make h as close to 0 as we possibly can. And that is what you're doing when you take the derivative. That is the essence of the mathematical operation called the derivative. There's different, so what I've written out here is different ways, different notations used to represent this operation of the derivative. You'll see this notation with a d over dx in front of the function that you want to find the derivative of at a specific value. D over dx is shorthand for find the derivative of. Even more shorthand is using the prime notation. F prime at a is find the derivative of the function f of x at the value x equals a. And as we just said, this is the limit as h goes to 0 of the change in y, f at a plus h minus f at a, divided by change in x, which in this case is h. All right, so on the next slide, we're going to evaluate this limit, actually find the derivative for a real function. In this case, the function is going to be y equals f of x, 3 minus 2x minus 4x squared, a polynomial function. So here we go. Again, the derivative of this function f at a specific value a is the limit as h goes to 0 of the function evaluated at a plus h minus the function evaluated at a divided by h. So let's apply this formula for our polynomial y equals 3 minus 2x minus 4x squared at x equals a. So what I do is I plug this polynomial in for f evaluated at a plus h, and anywhere there's an x, I put in a plus h. So that's this part right here. Then I plug in this function where f evaluated at a, where anywhere there's an x, I put in an a, divided by h. So the next step is to expand this out and simplify this expression and see what we get. So if I take this expression and expand it out, I get a big, long, messy thing that looks like this. And now what I can do is I see that there's actually a lot of terms in here. Let me get a red color. And you see there's a positive 3, negative 3, which will cancel. There's a negative 2a, positive 2a that cancels. And there's a, whoop, that was supposed to be a plus sign. There's a negative 4a squared and a positive 4a squared that cancels. So when you simplify this, you get the derivative of this function at a equals a limit as h goes to 0 of negative 2h minus 8ah minus 4h squared divided by h. So now I can divide, you notice how everything in the numerator has at least one h, so I can divide away the h in the denominator. When I do that, I get the limit as h goes to 0 of minus 2 minus 8a minus 4h. And if I look at this function, the h, the limit of 4h as h goes to 0 would be 0. So the derivative of f at a, f prime of a, is equal to minus 2 minus 8a. And it turns out you would get exactly the same formula for any a. So we can actually write out a general expression for the derivative of this function that we started with, 3 minus 2x minus 4a, or 4x squared, for any value of x. It's going to equal minus 2 minus 8x. So we find that the derivative of our original function, which again was this, 3 minus 2x minus 4x squared, the derivative of this function, f prime of x, is a different function. So now for any value of x, we can find the value of the function itself, or we can find the value of the slope of that function, the rate of change of that function at that same value. So again, the initial function we started with, f of x, was, here it's written a slightly different way, minus 4x squared minus 2x plus 3. And the derivative of that function at any value of x is minus 8x minus 2. And we found that derivative by applying the limit definition of a derivative. So if we look at polynomials in general as a class of functions, and we could do a bunch of different examples, and what we would see is a bunch of rules emerge for how you find the derivative of arbitrary polynomials. And I've summarized those rules on the slide here. The first rule is called the power rule. If you have a function that looks like x to the n power, the derivative, d over dx of that function, is n times x to the n minus 1 power. So we can see that up here in the term that's minus 4x squared. The derivative of the minus 4x squared term becomes 2 times the exponent, 2 times minus 4 times x to the first power, which is minus 8x. Another rule is that if you have this is called the constant multiple rule. If you have a function f of x that's multiplied by a constant c, the derivative of that is the constant c times the derivative of the function by itself. So the derivative of c f of x is equal to c times the derivative of f of x. And finally, the sum rule is if you have two functions f of x and g of x, and they're added together, then the derivative of that sum is the sum of the derivatives. So the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. So let's take a closer look at this function one last time and apply these rules. So the derivative with respect to x of minus 4x squared minus 2x plus 3, I can apply the sum rule. That's going to be the same as the derivative of minus 4x squared plus the derivative of minus 2x plus the derivative of 3. I'll add it together. That's the sum rule. That's this last rule applied. So now I'm going to apply the constant multiple rule. The derivative of minus 4x squared becomes minus 4 times the derivative of x squared. The derivative of minus 2x becomes minus 2 times the derivative of x, and here I've added a 1 as an exponent. X by itself is the same as x to the first power. The derivative of 3 is 3 times the derivative of x to the 0th power. I can imagine that there's an x to the 0th power next to the 3 here. X to the 0th power, of course, is 1. I'm starting to run out of space here, but now applying the power rule to each of these terms, minus 4 times the derivative of x squared becomes minus 4 times 2x to the first. Minus 2 times the derivative of x to the first power becomes minus 2, 1 times x to the 0th power. And 3 times the derivative of x to the 0th power becomes 3 times 0 times x to the minus first power. So the x to the 0th power is 1, so that term will go away. 0 times anything is 0, so actually, let me get a different color pen here, red. This whole term is going to go away because 0 times anything is 0, and x to the 0th power is 1. So if I simplify one last time, I get the derivative of this function with respect to x is minus 8x, that's the first term, minus 2, that's the second term. And that's what we found by applying the limit function. So in conclusion, this was a quick introduction to what a derivative is. The derivative is a mathematical operation that allows you to find the slope of a function or the infinitesimal rate of change of a function at a specific point. And then we took a closer look at how, in practice, you can find this slope by using a limit, where when you evaluate the limit for a polynomial, you end up with a set of relatively straightforward rules that you can apply to any polynomial in general to find its derivative. Those are the power rule, the constant multiple rule, and the sum rule. So when we applied those rules to our example function, minus 4x squared minus 2x plus 3, we found the derivative of that function to be minus 8x minus 2, which was exactly what we found when we evaluated the limit definition of the derivative for this function. All right, well, thanks for watching. I hope this was helpful, and remember, you can rewind and watch this as many times as you need.